This is a metal wire stretched over a meter ruler, and here I fixed on both ends. I'm using the internal voltage of this multimeter to feed this very simple circuit with just the resistance of a wire, and placing the one terminal here on a fixed point, and with the second one move along this wire and read the resistance for different length. So for this, I need to set the resistance on the lowest value on this dial, and as the length, take different lengths of this wire and measure the resistance. Then I'm going to record the resistance for each length, and then I will set up this table and use this table to draw a graph with resistance over length. I just described the principle behind this problem from October-November 2014, paper 21, question 3. This red line represents a wire stretched over a meter ruler. This box represents the multimeter with 9-volt internal battery. We have 2 terminals here from the multimeter. One go to a fixed point of this wire, and the second one we are going to place on different position of this meter ruler and read the resistance on this multimeter. Now for a length of 0.2 meter, the multimeter read 1.1 ohms. For 0.3 meter, the multimeter read 1.4. For 0.4 meter, the multimeter read 1.8. For 0.5, the multimeter read 2.4. For a length of 0.7, the multimeter read 3.1. And finally, for 0.86, the multimeter read 3.9. Now, these values, they were plotted on this graph. As you see here, for example, a length of 0.2 corresponds to a resistance of 1.1. For 0.3, it'll be about 1.4, and so on. So here we have 1, 2, 3, 4, 5, 6 points on this line. This is a structure question that is derived from a lab experiment. The objective of this lab experiment is to find the resistivity of this metal wire. I'm going to give you 3 visual observations of this graph. The first observation is that the points, they are scattered, not on the line. The resistance of the wire is displayed on the y-axis, and the units is ohms. And the length of the wire is displayed on the x-axis, and the unit is meter. If a structure question includes a graph with values I believe is expected to calculate the gradient or slope of this graph. And for this, we need to select 2 points and draw a big triangle. From the x-axis, I'm going to select 0.4 and 0.8. Now I'm going to find the corresponding on the y-axis. Make sure that you cross the line. I will have to make sure that where I cross this line right here, that I'm going to find the corresponding on the y-axis. To identify this intersection, I have to count here 3.1, 2, 3, 4, 5, 6, 7, 8, 9, 4. So this is 3.6. And this, because it's just one box below 2, this should be 1.9. So this is my triangle. After my graph analysis, now I'm going to proceed to answer the questions. Question A. The points shown in, this is the graph, do not line on the best fit line. Suggest a reason for this. This line is the best fit line, and the points, they are a little bit above or below the line, but not on the line. This is an indication of random error in measurements. This is caused by the experimenter. Could be parallax error or not align the instrument correctly, or even not take the measurement with a consistency. B. Determine the gradient of the line shown in the graph. Gradient and slope is the same thing, is the rise over the run. In this case, the rise is the y-axis, which is the resistance, the change in resistance, over the run is the x-axis, or the change in length. So my rise that corresponds to this triangle is the 3.6 minus 1.9. And my run is 0.8 minus 0.4. So the gradient is the change in resistance over the change in length. This is 4.25 ohms per meter. So that's the answer, is 4.25 ohms meter minus 1. Question C. The cross-sectional area of the wire is 0.12 square millimeter. Before I keep going, I have to look at the unit for this question, which is meter, and here I have square millimeter. So I'm going to use the multiplier to convert this to square meter. So in this case, is 0.12 times milli is 10 to the negative 3, because I'm converting to meter, and all this is square. Now in this step, I convert the milli, which is 10 to the negative 3, meter, in this case m. I'm going to square all. And now I multiply the exponent. 2 times 3 is 6, negative, and my meter now is square. Then I have converted square millimeter to square meter. The next statement, it says use your answer in B, which is this one, to determine the resistivity of the metal of the wire. The only formula that we have resistivity is this one, the resistance of a wire in terms of the length and its cross-sectional area. Now I'm going to rearrange this formula in terms of resistivity. So I have doing cross multiplication here, rho L is equal RA, then rho is RA over L. Perfect. I have R over L from B. Why? Because look at the units. Is resistance over length. So here is how I calculate the gradient. So the gradient of the line is 4.25 ohms per meter. So I'm going to replace this value right here. So rho is 4.25 ohms per meter times the cross-sectional area, which is 0.12 times 10 to the minus 6 square meter. Now let me explain this step. So R over L is my gradient, which is 4.25 ohms per meter, times the cross-sectional area, which is 0.12 times 10 to the negative 6 square meter. So I multiply the numerical values, and this is my result. And also I work with the units. I cancel here the meter with one of the square meter from the numerator. Now is left m, just 1 meter. So omega times m is omega m, which is the unit for resistivity. So it's possible to calculate the resistivity of a wire by get a length of the wire and measuring different segments and measuring the resistance of this wire, and use this data to calculate the gradient and use this formula to calculate the value of the resistivity of this wire. Last question. The resistance R of different wires is measured. The wires are of the same metal and same length, but have different cross-sectional areas A. On this figure, sketch a graph to show the variation with A of R. So what's going on in this problem? So we have here different wires now, and they have the same length. They are made of the same material, so they have the same resistivity. However, the cross-sectional area of these wires, they are different. So how we can determine the resistance in terms of this change of cross-sectional area? First, you need to bring the original formula for resistance in terms of length and cross-sectional area. So the resistance, I'm going to isolate everything, have the same material, same length, but different cross-sectional area. So I'm going to isolate the variables. They remain constant, and the one they are changing. So the resistance is inversely proportional to the cross-sectional area. What that means? If a cross-sectional area is larger, the resistance is smaller. If the cross-sectional area is getting small, the resistance is getting larger. I want to bring the analogy with resistance and cross-sectional area with this example here. In this case, we have two tunnels. One tunnel is wider than the other one, and you are trying to crawling through this tunnel. So the one that is really narrow, so you are going to is more difficult to crawl through and get out of that. So you have way more resistance. So narrow the cross-sectional area, larger the resistance. Here, and greater the cross-sectional area is the resistance is less. So how do we translate all these into a graph? Hint, look at this equation. So R is inversely proportional to a variable. So if we want to kind of translate into a graph equation, so that is the same as y is 1 over x. So this graph should look like this. Let me So be careful, do not touch the ends with the axis. Now here I'm showing 3 points on this line to indicate that as the area gets larger, so the resistance is getting smaller. So here is the resistance is high, the area is small. So as the area gets larger, the resistance is getting smaller. A structure question from October-November 2012, paper 21, question 2. Define electrical resistance. Is the ratio of voltage over current. So this is R, is V over I. 2B. A circuit is set up to measure the resistance R of a metal wire. The potential difference PD in voltage across the wire and the current I in the wire are to be measured. Draw a circuit diagram of the apparatus that could be used to make these measurements. This line represents the metal wire. To visualize the resistance of this wire, I'm going to represent with this box. That's the resistance of the wire, R. The problem states that we need to add a potential difference of voltage across the wire. So now I establish a voltage connected to the terminals of this wire. Now I have a current flowing through this wire because it's connected to the terminals of a battery. So now I can calculate the resistance of this wire, which will be the voltage divided by the current flowing through the wire. But the problem is asking to design a control experiment. The way that I have here, I will have a constant value of resistance because nothing's changing. To make sure that I'm going to change current and the voltage on this wire, I have to add a variable resistor. So this variable resistor is going to be manipulated. So I can have from start to increase little by little, and then the current is going to change and the voltage is going to change as I change the value of this variable resistor. Now I need meters. So the meters that can provide reading of the current and the voltage on the wire as this variable resistor change its value. I need a voltmeter connect in parallel with this wire. Also, I can use a multimeter on the voltmeter settings. And also I need a N meter connected in series with the circuit so I can read the current flowing through the circuit here. In this table, I select some points that I see in this graph that supposedly is part of this experiment. So as you manipulate the rheostat, and you can read current and voltage on the wire. So using data table, you can kind of draw a graph like this. But one thing that is interesting, that without any voltage 0, so there is a current already indicating in this ammeter, which is 0.05 amps. With the voltage of 1 volt, the current is 0.09, 2 volts, approximately 0.13 amps, 3 volts, approximately 0.19 amps, and so on. So this table is correlated to this graph right here. A couple of visual observations of this graph is that those points here this is the line of best fit, and those points, they are not on the line. They are a little bit above and below. And another factor is that there is a y-intercept on this graph, and the y-axis is indicating the current in amps, and the x-axis is indicating the voltage in volts. By definition, resistance is the ratio of voltage over current. For this reason, resistance is not determined by the gradient of this graph. Now, explain how the figure 2.1, which is the graph, indicates that the readings are subject to a systematic uncertainty and random uncertainties. The indication of a systematic uncertainty is that the y-intercept of 0.05 amps on the graph, which is due to instrument calibration. One indication that this line should pass through the origin is because with no voltage should not have any current. So voltage is 0, current is 0. But here is showing that voltage is 0 and the current is 0.05. So this is a calibration problem on the ammeter, possibly, that is going to shift the entire line up this much. So all this line is going to be shifted upward. For random uncertainties, a scatter of points above and below the best fit line. In this experiment, we have both systematic error indicated by the y-intercept and random error indicated by points above and below the best fit line. Next, use the data from the graph to determine R. Explain your working. To answer this question, since R is the ratio of voltage over current, I'm going to select a voltage on this graph. I'm going to select 2 volts. This one right here, that is going to cross this point. The intercept of 2 volts with the line of best fit and the corresponding value of y in this case is 0.14 amps. 2 volts with 0.14 amps. I chose the ratio V is equal to volts and I is 0.14 amps. So since I has zero error of plus a positive one, because intercept on the positive side of the y-axis of plus 0.05 amps, so my I is 0.14 minus 0.05, which is 0.09 amps. The next step is to calculate the value of R using the ratio between voltage and current. So 2 volts over 0.09 amps. So the resistance of this wire is 22 ohms. Next, in another experiment, a value of R is determined from the following data. The current is 0.64 plus minus 0.01 amps, and the PD over the voltage is 6.8 plus minus 0.1 volts. Calculate the value of R together with its uncertainty. Give your answer to an appropriate number of significant figures. First, calculate the value of R. So R is V over I. My V is 6.8. My I is 0.64. So the result is 10.625 ohms. Second, calculate the fractional uncertainty for R, which is equal to the fractional uncertainty of the variables of this formula. So this one here is this absolute uncertainty for V, which is 0.1, over the value of V, which is 6.8, plus the absolute uncertainty here for R, I, which is 0.01, over the value for I, which is 0.64. Okay, so now 0.0147 plus 0.0156 is 0.0303. Last step, calculate the absolute uncertainty for R. So this is, we know that we have this fractional uncertainty for resistance. So that means the absolute uncertainty is this value right here times the value of R, which is 625. So in this case, because the multiplier is R and R has a unit, so now the absolute uncertainty for R also has a unit. So the final answer is 10.6 and 0.3. To summarize, this structure question is about to find the resistance of a wire, set up an experiment, collect data, and identify sources. In summary, this question is about to find the resistance of a wire, set up an experiment, collect some data. So this is a hypothetical situation that with data here that was developed to find the systematic uncertainty, random uncertainty, to find the value of R. Make sure that you understand that you need to deduct the value that is the value of the current, that because the meter calibration. Then at the end, Give an example of values for I and for current and voltage to find the calculated value of R and its absolute uncertainty.